Okay, guys. How'd we do?
What? Hopefully not too bad. Let's see.
Yes. 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 You got to think mechanistically. You can write anything. I didn't write anything. Everything was in my head. But you can even just draw out the mechanism. Alkene attacks H+. That's all we have here is H+. They cation here, right? And then Br attacks there. Boom. Okay. BH3. Alkene attacks boron. Where are we going to leave plus? There. What does the boron then throw at the plus? An H. So you're going to have an H here and a boron here, coming off that carbon. Then what does this do to the boron?
Magic.
Replaces it with an OH. So instead of a boron coming off, we've got an OH coming off. Okay? There's a good chance that some of you maybe got products with lost carbons, especially here. You got to pay attention to your carbons.
Yes.
Okay, over here, chloronium ion and then water attacks it. I drew a chloronium ion bolded, this would be dashed, or you could draw it the other way. Water then attacks, if that's bold, how does water come in?
Back.
Dashed. Ultimately, the OH and the chlorine are going to be trans because it comes in backside, okay? It would actually come in from the back and push the methyl forward. You get this, the OH and the chlorine trans, but the OH attacks here, right? Because that's where the plus would be if it actually formed. That's also where the plus is because that pulls more and you get more plus charge here because it can handle it more. Okay, so you have regiochemistry, you also have the OHCl trans, that's the product. Of course, you could get the enantiomer and you can maybe say, well, these two could be dashed and that could be bold. I only showed relative stereochemistry. That means I only showed that, hey, the OH and the Cl are trans. Yes, you could show that another way, but trans is, okay, where here the OH and the Cl are cis, that's wrong, and OH on the wrong carbon. How we do?
Very good so
Oxymercuration would give that product without any rearrangement. How we do?
What with H3O?
What about H3O?
I thought it was H3O. You just hydrogen would go on the top, which just go right here.
Okay, bad question. I'm sorry, H3O plus is also correct because you wouldn't expect any rearrangement anyway. Okay, sorry, bad question. H3O plus would give the product also without rearrangement. Okay, bad question. There's two answers, C and D are both correct. I made this new question up 10 minutes ago, and because you're going to get cation here, why would it rearrange? It's tertiary. Okay, sorry. Bad question. Two answers correct. Make sure you understand why the difference between C and D. Here there'd be no difference because it ain't going to rearrange anyway. Okay, which of the following alkenes is not the line circle? The line circle cannot have cis or trans. Okay? I mean, if you put the methyl group up here, it's the same compound. On the other hand, here, these groups are coming off trans of the double bond where you can make them cis, and that would be a different compound. Okay? The other three you can change. This can be cis or trans. Here the methyls are trans. I can also show a version where the methyls are cis. Those would be stereoisomers. Thus, the alkene is stereogenic. Okay? This alkene, its presence in this situation leads to stereochemistry. Well, that one does not. So that's a stereogenic site. We'll talk about more of that today. Okay? A chiral carbon is a stereogenic site. Because at a chiral carbon you can have R or S. At this alkene you can have cis or trans. Now the whole alkene is one stereogenic site, okay? Mechanism, okay? Just like we were thinking up top, alkene attacks H+, where are you going to leave cation? You're going to leave cation there, correct? So this swings over, attacks H+, makes a bond to the H, leave cation here.
Hydration.
Methanol could attack here, but that ain't going to give that product. We need a hydride shift. You need to draw the H in, you need to shift the electrons over, break them apart, break them from this carbon, move them over and bond them here. That leaves cation here. Now methanol can attack. We get methanol bonded, one lone pair left, positive charge. To go neutral, something needs to take the H. Bisulfate could take the H, leaving the lone pair behind, two lone pairs. And we can reform H2SO4, which was the catalyst. I would typically allow you to do this because it's complex, but of course bisulfate is this, and these electrons take the H. Okay? I'll usually just show it condensed for H2SO4. Or you can use water, because this is an aqueous acid. And really, what is this? This is really H3O+, right? That's what sulfuric acid is. If you want to use water, that's fine. But as I told you, I like to use the actual conjugate base so I can reform the actual acid structure. Okay, how do you do on the mechanism? Okay, this will be posted. Of course, make sure you don't make the same mistakes on the test, which is when? Monday. Yes, it's Monday. Okay. I'll offer a review session on Friday at 1, like the other Friday. This Friday at 1. Okay, stereochemistry. Any questions? Let's look at the white. We got the white and the blue. Let's look at the white. First page is some problems to be working. For example, the top right corner, it says, is that compound RS? Okay? Well, hopefully you recognize that you should be able to give a good attempt at that. We've covered that. Where maybe other ones, Fisher projection, we haven't covered that yet. It doesn't mean you can't be looking in your book and reading about Fisher projections. Okay. Let's look at a little more intro stuff, sort of set the stage. Back at the first page here. Is stereochemistry important?
Yes.
Well, heck yeah, it's important. For example, what's the difference between cellulose and starch? It's only stereochemistry. Actually, does this look familiar? That's a chair confirmation. It's just got an oxygen in the ring. But these are all the same. That's actually the same. The only difference is this is a polymer. Okay, it keeps going. The polymeric. That's the same. This over here is the only difference. Here, that is equatorial, or you can say it's up, where here, it's down. That's analogous to maybe this being bolded and this being dashed. This is up, that's down. Or it's analogous to forward or back, right? Two options. Now this also has the option of axial versus equatorial and things like that. That's the only difference between the two. Thus, they're stereoisomers. They have the same connectivity, it's just different projection at one bond. Okay? Well, does that make a difference? Makes a huge difference. Our bodies can digest starch, but our bodies cannot digest cellulose. Makes a huge difference. If we could digest cellulose, we could eat trees and stuff, and we would not have as much concern with famine. I think that's right. Okay, well we can. Stereochemistry is huge. It's very important. Here's something you need to be referring to. Okay, we talked about constitutional, stereo, etc. Okay, this is a flow chart that clarifies all this. Isomers. two types, constitutional versus stereo. Okay? We've already really covered this. There's actually two types of stereoisomers, enantiomers and diastereomers. Enantiomers are mirror images that are different. Because if they were the same, they would not be isomers. They'd be the same thing. Okay? Mirror images that are different. Terminology, RS or D or L. You know, you have to know the difference between. RS applies to a certain carbon, the configuration around a certain carbon. D or L is the molecule as a whole. We'll say more about it. The other is diastereomers. That's almost a default. If they're stereoisomers but not mirror images, then they're diastereomers. Stereoisomers that are not mirror images. Cis and trans is actually a type of diastereomer. Okay? I used to get to the end of Organic 2 and students never realized that cis and trans are diastereomers. So I had to put this in here. But look, if we look at this, that versus this, that's cis and trans, right? Okay, let's go back. Are these isomers? Sure, they both have the same formula. Okay, are they constitutional or stereo?
Stereo.
Well, they have the same connectivity. Chlorine attached to carbon 1, chlorine attached to carbon 2. Okay, it's the same connectivity. So they're stereoisomers. Well, are they mirror images? No. The mirror image of cis, okay, you be my mirror. I'm looking in the mirror. I'm cis, because that's trans. Okay? And you're my mirror, so if I'm cis, what are you? No, you got your arms pointed. Now this is trans. Okay? Go home, look in the mirror, and hold your arms cis as the same sex. This would be trans. And look in the mirror. Your mirror image is also going to be cis. If you look in the mirror and you're staying like this, and you look in the mirror and your mirror image is like this, let me know. we got something going on. The mirror image of cis is cis. These are not mirror images. I mean, if I drew a mirror here, that looks in the mirror and sees that. Okay? So, there's stereoisomers that are not mirror images. What are they? They're called diastereomers. Cis and trans is a type of diastereomer. We'll also learn erythro-trio. Okay? So, trust that flow chart. Another reason why stereochemistry is important, a variety of reasons. Here's a drug that was called thalidomide. Here's the structure. How many chiral carbons in the compound? One chiral carbon. None of the others are chiral. Okay? By the way, usually chiral carbons you see the dash in the bold. Okay. Why are they not showing any dashed or bold here?
2 hydrogens and the carbon.
Well, there's 2 H's. It's not chiral. It don't matter. You can draw the bonds however you want. So they didn't take the time to draw them in. Okay. Now, I could show this structure without that being. I could just show the bond there and ask you still to identify that as chiral. Okay. That's shown as a mirror image, right? Okay. First off, which is S and which is R? Let's do the practice here. This one over here, is this S or R?
R.
Okay, what's on that carbon? Boom, 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 and then I draw an H. What's high priority?
Hydrogen.
Hydrogen. What's next?
CO.
Carbon or carbon? Well, we got to keep going. What's attached to this carbon?
Oxygen.
Let's draw the 3 things attached to that carbon. Oxygen, oxygen, and nitrogen. When it's double bonded, it's like it's attached to it twice. This carbon is attached to what? Carbon, hydrogen, and hydrogen. Okay? You list the high priority thing first as you go across. Right here we get the winner. O beats carbon. That's 2. This is 3. The H is here. How's it projected?
Cold.
Forward.
Should be
So that's 4.
R.
It's clockwise. It's not R.
S.
The H is coming forward, so what do we do?
Reverse.
Reverse it. That's S. I bet you $100 that's R. Okay? Because it is the mirror image. I can tell it's mirroring. It should be R. Do it yourself, make sure. Okay? Now, thalidomide, the R compound is safe. This drug was used in the late 50s and 60s to treat morning sickness in pregnant women, especially in Europe. Okay, some in the United States. R is safe. S, teratogen, cause defects to the developing fetus. Okay? When the research was going on, they made R, they tested R, but when they started manufacturing it, somehow they started manufacturing both. It's like a racemic mixture, 50-50 mix. And the S is actually a toxic teratogen, where R is not. It led to birth defects, and it led to babies being born without arms and stuff, and this is a photo of some of them with really no arms. They were called thalidomide babies. It was basically bad science, bad manufacturing of a chiral compound. Eventually, an American nurse sort of focused on this and helped figure out what was going on, and then John F. Kennedy gave her an award. So, stereochemistry is very important. On the other picture, on the other side, some miscellaneous things. We talked about how a chiral compound fits into a receptor, where one may and in the mirror image may not. That's sort of illustrating this, so you can look at it. There's some drugs up top. Ibuprofen is actually, well, that's S. You can use these as practice. That's Prozac. That's R. Make sure you know that's R. Prozac is always R. Here's one thing I really want to make sure you see here is look at this big compound. The drug for prostate cancer, pretty large structure. I could ask you how many chiral carbons are in this compound. Maybe it would take a while to count them up. Okay. How many stereogenic sites? Here's the name. I can ask you to name it. Okay. Stereochemical descriptor. They put all of the RS descriptors in the front. Because everyone is set, it's specific one. 1S, 2S, 3R, 4S, 7R, 9S. Okay? But ultimately, this compound, here's the specific rotation. Negative 32.9 when it's dissolved in methanol. That's the rotation. Since it's negative, it's the L enantiomer. So that's the L enantiomer. See, L is for a compound as a whole, where RS is for an individual carbon. Okay? What would the D enantiomer look like? Or how would the D enantiomer differ?
All the wedges and dashes flipped.
The D enantiomer would be the mirror image, and in the mirror image, everything is reversed. So the D enantiomer would actually be R, R, S, R, S, R, R, S, R. Okay? When you look in the mirror, everything's reversed. When you go home tonight, look in the mirror and hold up your right hand. And your mirror image will be holding up the left hand. Okay? Here we go, mirror me. That's not mirror. If I look in the mirror, I'm going to see an arm over here up. Right? I know it's reversed. If I look in the mirror, I want to see me looking back with this arm up. Okay. I've got my right arm up. You've got your, you've actually got your left arm up. Okay? When you look in the mirror, everything's reversed. All right? So, some just miscellaneous examples. I want to point out a few things. Let's get back to where we left off at. Questions? More on optical activity. Okay, I'm pretty sure I can go ahead and say I think we're going to skip the polarimetry lab, which is set for Monday, Tuesday on the syllabus. No, I'm sorry, it's actually set for today and tomorrow on the syllabus. Okay? We pushed everything ahead, so we would be doing it Monday, Tuesday. But we're not going to do it Monday, Tuesday. Instead, we're going to do what's on the syllabus for Monday, Tuesday. And what is that?
Hexine.
It's a hexine, an alkyne, and it's also a group project. Is that what it says? Yes. Monday, Tuesday will be the group project, as listed on the syllabus outline for that day. So we're getting back on schedule by not doing polarimetry lab. Okay? Now, polarimetry, what we're talking about here is determining the optical activity, the optical rotation of an optically active compound. You would use a polarimeter. Plug this in, power source, there's a bulb in here that generates plane polarized light. Okay? First off, you dissolve your compound or your mixture of compounds in a polarimetry tube. Both ends will come off. Pour your solution in there, and then the liquid's in here. Both ends are open, and you can see light through it. Yes, I see the light. Okay, light goes through the tube, and this goes through the solution. You put this in here. You close that up. You turn the light on. It goes through that solution, and you look through here, and you see how the light is rotating. There's a mechanism for showing you that. You can look in the lab if you want to see what this mechanism looks like. Then you rotate the dial one way or the other. Okay? You rotate this until you get what's called the reading. If you rotate to the right, that means the light's been rotated to the right, according to my eye. And then you get a reading. For example, minus 32.9 or whatever that was for that big drug. Of course, minus would be to the left, correct? That would be if it rotated it this way. Now, if this was a racemic mixture, would you expect any rotation? No, no. It would be zero. It wouldn't do anything to the light. What if it was just ethanol in the tube? Would that rotate? No. Would you expect ethanol to be optically active? No. Only a chiral compound is optically active. Okay? Not something like ethanol. That's a polarimetry tube. Let's look at questions. Okay. Already said that racemic mixture is not optically active. Sometimes that's just called racemic. Sometimes you may see it called a racemate. Okay? It all means racemic mixture. An antinomeric excess. Number 2. I know it's a little dim. Again, usually these show up well. Something about this really projected colored paper. Okay, you got it in front of you, number 2. An antinomeric excess is a common way of describing essentially the ratio when you have a mixture, other than 50-50. A 50-50 mixture is called racemic. Now, what if it's 60-40? Like, okay, D to L, right? Well, you could say I have a 60-40 mix, and people will know what you're talking about, 60%, 40%. But there's another way to describe that. It's called an enantiomeric excess. The enantiomeric excess is the excess of one enantiomer that exists beyond racemic. you can read this and then you're going to read it and say, what? Well, let me tell you the what part. Okay. Hopefully this is a different example than I do there. What if you had 60-40? What would the EE be? Well, 40 of that cancels how much of the other? 40. See, this cancels each other. So I call that racemic. Now, what's left beyond racemic?
20D.
20 of this one, because that's 40 and 20 equals 60. Okay. After these cancel, what are you left with?
Percent.
20. Okay. So the EE equals 20%. This is what's left after part cancels part, after racemic. Now it's also just the difference in the two, because that's 20% more than 40 in terms of a whole number. Maybe try to do math, you'll say, isn't 60 50% more than 40? Because 50% that's 20, that's 50% more than 40. No, this is actually just the difference in the two numbers is 20, and it's 20% EE. Okay? Now, I try to describe this to you. If you want formulas for doing this, look in your textbook. I'm trying to explain what the formulas mean. Okay? 20%. In the one I gave here, I tried to give an example. A mixture that has, I'm doing it backwards. If it has an EE of 10% R, don't look at the answer. If the EE is 10% R, what is the ratio?
55.
Did you figure that out?
55, 45.
Did you look at it?
No.
Yeah, it'd be 55-45. First off, it's 10% difference. But how do you get this? Because 10% is what's left after it's racemic. So I can say, let's see, that means 90 is racemic and 10% is left. Right? And the 90, half and half, so it's 45, 45. And then I got 10 left. But the 10 left adds with one of the 45s to make it 55, 45. Okay? 45, 45 would be racemic, 10 left. But this is the excess. The excess is R. So this would be RS. You got 10% R left. 45 and 10 equals 55. Okay. There we go. Let's do another example. What is the ratio of D to L isomers in a mixture that has an EE of 60% D?
90, 10. 80,
60% D. Yeah, it's 80-20. Okay? You can figure this out in your mind any way you want, as long as you get the right answer. If we go backwards, it's 80-20. We would say, hey, if 80-20 of what? Which is which?
80, D, 20.
Ratio of D to L. Got more D. This is D to L, right? It's the excess of D. Now see, if you look at racemic, 20 of this would cancel 20 of that. And after 20 of this cancels 20 of that, what are you left with of this? You're left with 60. And that's ultimately what that means. I said it's the amount that's left after racemic cancellation. Okay? What is the EE of a sample that is 70-30 DL? That is 70% one, 30% the other. What's the EE?
40%.
Yeah, it's 40%. If we go backwards, 40% is what's left after the other 60% is racemic. So it's like 30%, 30% cancels. And cancels, what are you left with? You're left with 40%. EO sounds, D is greater, so that's D, that's D, that's L. 30L cancels 30D. You're thus left with 40D. If you go back and look what you had from the beginning, you had 70D, 30L. Which is what the question told you, starting with. Okay, let's look at it another way. Let's bring in optical activity. That is, how might I know that I have a 70-30 DL? Well, optical activity can tell you that. You'd first need to know what the absolute value is for a pure enantiomer. For example, the one I showed, a big compound, wasn't it negative 32.9?
Yes,
Maybe?
Think so.
Let's say it's negative 32.9.
that's good.
Okay? So if I had some of that compound, and I said, hey, this is just pure D-isomer, or whichever one it was. Hold on, if it's negative, that means it's L. Okay?
Negative 32.9.
If negative,
Yeah.
means it's L. So if I got that compound, and I say, hey, is this pure L compound? Well, I should be able to do a polarimetry, and I should get what? Negative 32.9. Of course, somebody's already done that and listed that as a good value.
Yeah. How would you get a pure enantiomer?
That's a great question. I don't think we'll ever talk about that. It's a good question,
Okay.
but it can be done.
Yeah. Okay.
I mean, many drugs are just one enantiomer. Since you asked that question, will recrystallization separate enantiomers? Do enantiomers have the same solubility?
Yes.
Yeah, same solubility. So why would one crystallize and the other one not? Well, in general, it would not. Okay, because recrystallization you're taking advantage of different solubilities. This one will crystallize where the other one stays dissolved. Why would one enantiomer recrystallize and the other not? They have the same solubility, they have the same density. Okay.
Supposing your solvent is chiral.
There's many things. You can also get, Louis Pasteur actually observed crystals forming an enantiomer. But it's a specific reason that's beyond what we can talk about here.
Okay.
In the end, it is difficult. You usually have to do some very specialized technique, like use a chiral medium, like a chiral solvent or a chiral stationary phase. Okay, a little bit beyond this. But how do I know what if I have is pure? I can do polarimetry and get negative 32.9. What if I do polarimetry and I get 0? What does that suggest about my compound? It seems like I got a 50-50 mix of both D and L. But what if I do polarimetry instead of negative 32.9, I get negative 10?
Small d.
I do have more D, but what's the percentage? You know, what's the EE? Because that's a common term.
10 over 32.
I'm not sure. Let's see. This is how you do that. Okay? What would be the degree of optical activity, that is, what's the specific rotation of a 60-40 mix of 2-butanol? By the way, we did 2-butanol. What's the rotation of 2-butanol?
13.5.
13.5? R and S. This is R. Was R plus or minus?
I was out.
R was L, so that would be this one. Okay. We know this is plus. Now, if it's 100% one of these, we get one of these. And if it's 50-50, we know the answer would be 0. So what do we get if it's a 60-40 mix? Well, here's how you do it. You may be on this. First off, what's the EE? 20% EE, right? Now, that means 40 cancels 40, and what are you left with? 20. Of which one? Which one's the major one? R, 60-40. So this is R, R, S. 40 of S cancels 40 of R. You're left with 20 R. This is what rotates. You only get 20% of max. Because the other portion cancel each other out. You only get 20% of max. What's 20% of max? 20% of this. 10% would be 1.35. 20% would be 2.7. Yes, is it plus or negative? R, yeah. Minus 2.7. Okay, I'm losing a sig fig here because I got one more. That's okay, at least I didn't gain one. Be that. Because the EE is also the amount that rotates. It's actually the amount that rotates because the remainder cancels each other out. Okay? So you would expect negative 2.7 of such a mix. Let's do it the other way, though. I believe this is going to be the other way. Let's look at A here. What is the EE of a random sample of 2-butanol, which could be two different stereoisomers, right? If the specific rotation was measured to be negative 10.13, yeah. You may have already seen the math. If it works for you, you're good. But what you're saying is confusing me because I'm like, I have it in my own mind. Okay? So let me tell you how I do it. Okay, what is the EE? If we kind of go backwards here, this is what percent of max? Max was what?
75%.
This is what percent of max?
75.
What? Is that 75% of this?
Yes.
You need a calculator.
Yeah.
It's probably some whole number. That's why I gave you 10.43. It looks like about 75%. Is it? Okay. 75% of max. Now, the plus or minus doesn't matter right now. It's a whole number. I mean, what do you call it? Not a whole number, but
Integer value.
what do you call it when the plus or minus doesn't matter? It's a absolute number.
Yeah, absolute value.
Okay. 75% of max. So what's the EE?
75.
Yeah, it's actually 75%. Because the EE gives a rotation. Because the EE is what's left over after receiving. You got something canceled out. What's left over is the EE. Also, what's left over is what rotates. So if the EE is 75%, what's the ratio? What's the ratio? Is it 75-25? No.
87.5, 12.5.
Be 85, 50, no.
87.5.
87.5 to get
87.5 to 12.5. Because in the ratio, if 12.5 cancels 12.5 of this, what are you left with?
75.
You're left with 75. So this is your ratio. Which one is 87.5? Somebody said R. D. It was predominantly minus, so it's predominantly the L one. Which one is L? Okay. I assume we got that correct. 87.5, 12.5. You can do this the other way. You can start here, and you should be able to get back to this number. Okay? So, that's how your optical activity can tell you about the composition of your enantiomers. Okay, Fisher projections. Questions while I'm racing about optical activity? Now, hopefully, when you read the book chapter about all this and you see hey, they show you how to work the formulas, you'll understand what they're doing, and it's not just numbers to you. Okay. We did Fisher projection in here. Fisher projection is where we do crosshairs to show the chiral carbon. We got one chiral carbon with 4 substituents. Chiral carbon is going to be the 4 substituents. We would draw in the H. You always draw in the H's of your Fisher and your Newman doesn't have to. Newman has to have H's. Sharon Boat does not have to have H's, unless the instructor asks you to draw. Okay, but a Fisher you always need to draw in the H. Otherwise, it's going to look like a nothing. Okay. The things on the side, are they coming out or going back?
Out.
Things on the side are coming out, hugging you, or like a bow tie. Top and bottom is going back. Okay? It's easiest to do these with the things that are back and forward on the sides. And since they're on the sides and they're coming out, here's the board. Okay, it's like this. There's the board. These are coming out. I want to stand here and look through here. Okay? Well, the chlorine's coming towards you guys, so it's on my left. I see a chlorine coming to the left. Okay, the chlorine's on the left. Looking through there. The bromine's going behind the board. So if I'm looking through here, the bromine's on my right. What's on the carbon going straight up?
Nothing.
Nothing. Now, you might want to clarify that because it looks a little, that's why I often draw an ME or something. That's a CH3 on the end. What's going straight down? And actually also away from me. Yeah, that's the H. It's also going away from you, right? So is the method. So here's the board. The method's going up, but it's also going a little bit away from the board. It's actually going away from us, right? So there's the Fisher. Now it's much easier to then tell R and S. Because really, if you try to tell R and S from here, you have to tackle 2 things at the same time. First, you have to get your view right. Then you have to say, okay, while I'm thinking what the view is, now I got to do R and S. Don't do it that way. First, get your view right. And this is a better view. Now do R and S. 1, 2, carbon is 3. It's clockwise. How's the H? Going back. So what is it?
R.
R. See, it's much easier to do. Okay. Also, this is also going to be difficult to do R and S because the H is not forward or back. If the H is back, we just do 1, 2, 3 and say it's whatever. If the H is forward, we know we do 1, 2, 3 and then just reverse what we saw. But what do you do when it's in the plane? Well, you could do a variety of ways. I'm suggesting draw it in a fissure and then do it. Because when you draw it in a fissure, you're actually doing a different view. Now the H is either forward or back. In this case, it's back. Okay? So drawing it this way gives you, it's a convenience, and that's why it was developed, this method of, I think some guy named Fisher developed this. Okay? I think this was Emil Fisher who did a lot of different stuff. Okay, let's move on to compounds with more than one chiral carbon. This thing is light for a second and then dark. I don't understand. Here's one here. How many chiral carbons?
2.
Actually 2. How many stereoisomers are possible for this compound?
4.
4.
How do you know it's 4, Sim?
2 over n, so just 2 over, 2 to the power 2.
2 to the nth power?
Mm-hmm.
How did you figure that?
I know.
You knew that? How'd you know that?
I'm studying for DET, that's why.
Okay. Yeah. How many? It's 2 to the nth power. Where n equals what?
Number of carbons.
Number of stereogenic sites. Now, give me examples of stereogenic sites.
Alkenes.
Chiral carbons. Do you know any other examples of stereogenic sites?
Alkenes.
Alkenes.
Alkanes.
Okay? So it's not just number of chiral carbons. That's kind of specific. Okay? Do you see any other stereogenic sites in this concept? No. So this is 2 to the 2 equals 4. All right. Two to the n is the maximum number. There will be cases where it will be less than that. Okay? We'll have to figure out when it may be less. But it can't be more. Okay? So 4. All right, we'll draw them all. Draw all 4 of them. Let me maybe do it on the board because we're going to work from what I draw. But could you draw all 4?
Mm-hmm.
There's a backbone. Let's make the OH bold. Because see this projection around this carbon can be 2 different ways. We can illustrate that by maybe showing the OH bold. Same thing over here. Let's draw the chlorine bold. Now we have one specific. Now let's go boom, boom, boom. Let's draw the OH bold. And let's draw the chlorine dash. Let's draw the OH dash. Jacob, what do you want to draw here? Dash or bold?
Dash.
Okay. It really does not matter because that's going to... Now, what would be the 4th one? This, there, and this what?
Bold.
And that bold. Can we do any more?
No.
Based on the math, no. Based on structure, I mean, how can you do another one? Let's see. Okay, RS. Is this RS?
R.
R.
Brandon? RS. R. O, carbon with chlorine, carbon with H's, H in the back. Yeah, R. RS. Carrington? What's high priority group on this carbon? Chlorine. What's next?
The
Carbon with O or carbon with only H's?
carbon with the O.
There. H in the back. What is this?
R.
R. Okay. Now do the rest of them. Okay. Here we go. What is this one?
R.
R. What is this one?
S.
S. What is this one?
S.
S.
What is this one?
S.
What is this one?
S.
R.
R.
Yeah. The backbone is the same. If the backbone's the same, whenever I switch the projection, that should be S. Now, if you want to prove, you can sit down and say, hey, is that really S? And prove that it is. I bet you $100 that we got them all right. As long as we got the first two right, the rest are.
If you asked us to draw this out, could you do the same thing as, I guess, Newman?
If you want to put those in Newman's, you could.
I mean, would that be correct, like, if you asked that? Because that's
I
what
would
they did.
recommend it. So it's probably going to take too long. But certainly, you could draw this in Newman. And as long as it was the same compound, as long as both stereocenters were S and R, it would be right. But Newman's just another way to show it. I don't know why you'd want to show it in the Newman. Okay, there are your four. What's the relationship between these four? Well, they're all stereoisomers, but there's two types of stereoisomers. Enantiomers. Okay. This one. Which one of those is the enantiomer
Third
of
one.
this?
The third one.
Third one.
These two are enantiomers. Those are mirror images. Now they're not drawn as if they're mirroring. If you want to draw them as if they're mirroring, you can switch it around and. But isn't the mirror image where everything is switched? The mirror image, what's the mirror image of R? That's S. Trust me, it is. I mean, that's it's just, it's going to be ours. You can prove it to yourself. Okay. Where's the enantiomer of this one?
All right.
Those are enantiomers. Okay. Let's call these 1, 2, 3, and 4. So 1 and 3 are enantiomers. 1 and 3, do you expect the same boiling point or melting point for 1 and 3?
Yes.
You expect the same density? You expect the same everything except what?
Optical.
Except rotation of PP light. One of 1 and 3 will rotate to the left and the other to the right. I don't know what magnitude. It may be plus or minus 5 or maybe plus or minus 79. I don't know. 1 and 3, which one's D, 1 or 3? We don't know unless you have the information. But is one of them D and one of them L? Yes. That's why it's called a DL pair. Okay? One is D and one is L. I don't know which is which. But if I got them there and if I'm talking about it, I can call it a DL pair. Yep. We got 2 DL pairs on the board. 1 and 3 is a DL pair, 2 and 4 is a DL pair. What's the relationship between 1 and 2?
Diastereomer.
Are they isomers?
Yes.
Yeah, they have the same form. Add it up, they're the same. Okay, are they constitutional or stereo? Do they have the same connectivity or not? You got an OH connected to the second carbon, boom. You got a chlorine attached to the third carbon, boom. Things are connected to the same sites. What's the difference? Only the projection. Here, both are projected forward. Here, one is forward, the other is back. What type of isomers are they? They're stereoisomers. There's two types of stereoisomers. Enantiomers. Are these enantiomers?
No.
No. Enantiomer of RR is not RS. When this looks in the mirror, everything has to change. So they're not stereoisomers. So by default, what are they? Diastereomers. We call those diastereomers of each other. Now, 1 and 2, do you expect those to have the same melting point, boiling point, density? No. Diastereomers have very different properties. Okay? We looked at that before when we looked at, you don't need to write this down, you've got this already. Do these have the same polarity?
No.
That was polar and nonpolar. These are diastereomers. They got very different melting points. And in the lab you're going to be doing today and tomorrow, you'll see diastereomers with melting points 100 degrees different. Diastereomers can be totally different properties. Because this guy, they're both coming forward. This guy, they're like this. That can make it hugely different. Now, you can rotate this. If I rotated this, let me show you that. If you rotate that, I could get to boom, 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 have this rotated down. This hasn't changed. What would this be? Chlorine back, if I rotate this, it's actually going to come forward, and this would be like that. This is 2, just shown a different way. Rotate. You got to know that. What's one way to know that? Do R and S. This is R. What is this? Chlorine's 1. Carbon with OH is 2. Methyl's 3. H is in the back. So what is this? S. Just like that. It's RS. Same connectivity, same projection around the carbon. Okay? Well, this one is trans and this one is cis. So which is it? What I'm getting at here is when you have free rotation, cis and trans does not work. You got to be careful about saying, hey, this is trans. Because I could draw it like that and then it's cis. So, you see that? That's sort of like with EZ, nomenclature for alkenes. This doesn't, cis and trans doesn't work with alkenes up to a certain point. So what can we call these? We need to give them a name to distinguish these, but it's not going to be cis and trans. It's going to be erythro and threo. To do that, that comes from the Fischer projection. What we want to do now, let me make sure we're done talking here, is we want to draw all of these in the Fischer projection. Anything else to discuss here? Of course, what's the relationship between 3 and 4?
Diastereomer.
Now, those are also diastereomers. But that set of diastereomers is really not, I don't know if you can really call it a set, but we've already talked about it. Diastereomers have different properties. Anything else to discuss here? Any questions about here? We're going to draw Fisher projections now. Let's draw a Fisher projection of number 1. Me pointing this out is going to be kind of relevant to the lab today. Okay, you've got to be careful about calling things cis or trans. You've got to understand the free rotation. Importantly, you can always just do R and S. See what you got. Okay, Fisher projection of 1. We got 2 chiral carbons. So we're going to need 2 fish hairs. And we're actually going to do boom, boom. 2 chiral carbons adjacent to each other. We number the total carbons. In terms of nomenclature, that would actually be 1 because chlorine comes before it, right? I'm going to say that's 1, 2, 3, 4. 1, 2, 3, 4. But only 2 and 3 are chiral. Now this is the N-methyl. It's going back, correct? And it's up away from the floor. I want to look at this with carbon 2 here, with the methyl going away from me. So where do I need to stand? I need to stand over here, and here's the floor. That is, carbon 2 is away from the floor. Which is closer to the floor? There's the floor. 2 or 3? 3. 3 is closer to the floor. 3 is closer to the floor. Okay? Look through here. With the methyl going away, is the OH on my left or right? I'm looking right here. Let's do a model of this. The OH is coming towards you guys. It's bold. So it's on my left. Let's do a model real quick. We got a 4-carbon backbone. Boom, boom, boom. OH is, let's call OH blue, like water. Going forward. And let's call chlorine green. Backbone is in the plane. Here's the board. Chlorine is coming towards you, a little bit down. The OH is coming towards you, but a little bit up. Okay? There that is on the board. Okay? I want to look through here at carbon 1. I'm just going to turn it up a little bit. What do I see? I see a methyl going away. The OH is on mine. I want to draw what I see. Okay? If I turn, I want to draw this. I want to draw this. See the methyl going back. It's also going a little up, okay? You don't get exact orientation here. But the OH is on the left. That means what's on the right? What's going back on this carbon? H. We need to draw that in. Okay? I just like to have methyls. It just looks more complete. That's a methyl on the end. Now, here we go. I'm going to take the model away. Carbon 4 is going away from us. I need to stand with carbon 4 going away, so I need to come over here and stand. But I got to keep my feet on the ground. If I look through here, okay, here it is on the board. But now I've come over here and looking at carbon over here. Turn it up a little bit. The methyl's going away. With the methyl going away, the chlorine is on my right. With the methyl going away, chlorine is on the right. The H is over here because the H is going the other way. Now look at, with the methyl going away, the H is on my left. Okay. Now your book may say rotate this. I do not recommend rotating. Instead, walk over here and look this way. Okay? We'll do some more of these. And there's a methyl here. This is compound 1. All right? How could we check ourselves? Well, it should be RR. And the same connectivity, but yeah. Is this indeed R? 1, 2, 3. Counterclockwise, H is forward because it's on the side. So what is this? R. Good, we got it right. How about down here? Chlorine is 1. Carbon with OH is 2. Methyl is 3. Counterclockwise, but the H is coming forward, so what is this? R. We got it right. Same compound. You can check yourself. There's the compound in a Fischer projection, 2 carbons. Okay. Draw compound 2, 3, and 4 in Fischer projections. And if you want to run, take a break, I'll give you a minute or two to work on these. Draw compound 2, 3, and 4 in Fischer projections. Okay. Question? This H is coming forward. We had 1, 2, 3 counterclockwise.
I was ignoring the carbon. I was saying 1 methyl hydro. I got it.
No, this carbon is attached to 4 things. You got to give all 4 things priority.
Yeah.
A carbon with a chlorine is going to be a higher priority than a carbon with just H's.
Can you explain again how did you put the chlorine on the right instead of to the left?
This methyl, is it going away from you or toward you? Right here, this one. The methyl's going away. Things at top and bottom are going away. So I'm drawing this with the methyl away.
Oh, okay.
With the methyl away, the chlorine's on the right. So I want to look at this with that methyl going away. I can't stand over here because from the carbon, the methyl is coming towards me. So I stand over here. The methyl is going away. See, that 4 is going away from this carbon. And with it going away, the chlorine, how is it projected? Back or
Got it.
chlorine's towards you. So if I'm over here and the chlorine is towards you, it's on my right. So with the methyl going away, the chlorine's on the right. With the methyl going away, the chlorine's on the right. There's a couple of tricks to do this without what I did. I've seen some students just do this and say, hey, it's RR. So I'm going to put these around and make sure it's R. I got a methyl, an OH, and an H. If we want the H on the side, I could draw it up here. We'll learn how to rotate. So if this is going to be R, if I put the OH here and the methyl here, is that R? Well, that's 1, 2, 3. So the H is coming forward. No, that's not R. So if I switch these, put the methyl here, and the OH here, is that R? 1, 2, 3, H coming forward, reverse. Yeah, okay, that's R. That's all you do. So that's one way to do it. You see what I just did? I just drew it and made sure it was R. Because that's what I'm doing. I'm redrawing it as R. But it would be good if you can learn how to look at it like I'm doing. That's what I'm going to do. You can look at things 3D, it'll help you with other things down the road. The other way to cheat here is, since we did the first one, the other three should be easy. But that's really cheating because, just like here, once we did RR there, these are easy. But don't rely on that, because then you don't. Okay. I think I'm going to try to keep these up here. Is this bold?
Mm-hmm.
Okay, that's 1. Okay, I think I'm going to start by doing 3. And I'm going to draw 3 right here. Okay. One and 3 are mirror images. If you just looked at these two, okay, I'll get started back with official. Okay. All right, let's do 1 and 3. Let's do official for 3. First off, if you looked at 1 and 3, can you quickly tell they're mirror images? Now, if you do RR and that's SS, then you know they're. But can you just look at them and tell quickly that they're mirror images? I couldn't. I'd have to think about it a little bit. Let's do 3 in a fissure. Okay? Fissure is always like this, 2 crosshairs. By the way, if you had 6 chiral carbons, you would do 6 crosshairs. You'll see such compounds in biochemistry. Okay? And if we turn over, maybe you don't even need to turn. Let me just show you. Here are your carbohydrates. For example, glucose. Well, it's not 6 chiral carbons. 4 chiral carbons. See, these are drawn in Fischer projections. And this OH is coming forward or going back?
Forward.
Forward, okay? Carbohydrates are drawn in Fischer projections. Okay? And then you have different ones. These are all stereoisomers. We'll look back at this a little bit later. Okay? Okay, I'm going to do it as if I'm looking fresh. Okay? 1, 2, 3, 4. Carbon 1 at the top. Okay, carbon 4 at the bottom. That is, carbon 2 is where the OH is. I'm going to put an OH here. Oh, by the way, in your Fischer projections, typically it's standard to put alkyl groups at top and bottom. And like substituents on sides. Now we can rotate, but let me just say this. So compound, we're going to do compound 3. With carbon 1 going away, we're going to have to stand over here. This is the ground. This carbon is closer to the ground, correct? 1, 2, 3, closer to the ground. Look through here. With carbon 1 going away, what side is the OH on? Mackenzie? Correct. It's going behind the wall. That's what the dash means. If I'm over here, behind the wall is on my right. So the methyl going away, the OH is on the right. What's on the left on this carbon coming towards you? If I'm over here, the H is on the left. Why am I over here? Because only by being over here is this carbon going away from me. Okay? H. We'll draw that methyl in. Now let's look at the next carbon. Is the carbon on my right or left? Is the chlorine on my right or left? Well, do I need to stand over here?
No.
No, I need to stand over here. The methyl going away. Okay, that methyl 4 is going away. When it's going away, the chlorine is on my, it's going behind the wall, so it's left. With the methyl going away, the chlorine is on the left. And there's an H coming forward. Here's compound number 3. There's 1 and 3 next to each other. Let me ask you now. Can you tell their mirror images now? Chlorine coming towards each other, OH going away. One of the powers of the Fisher projection is it's much easier to see things like mirror imaging. It's also much easier to find planes of symmetry once we start doing that. Okay? These are enantiomers. This is 1 and 3. Okay, I think I'm going to erase here. 2 and 4. I'm going to do those to finish it up. I'm going to cheat. By cheating, we'll give you some more information here. This is going to be compound 2. What's the difference in compound 2? Is there a difference at the carbon with the OH? I mean, then what compared to 1? Is compound 2 different here? No, it's the same. Compound 1 and 2 is the same here. Compound 1 and 2 differ here. Yes. The chlorine in compound 1 was bolded.
Yes.
In compound 2, it's dashed. It's the opposite in compound 2. And in the Fisher, that means it's on the opposite over here. So for compound 2, it would have here, and we would have over here the H. So I kind of cheated, but there's compound 2. Now let's do compound 4. Is there a relationship? What's the relationship between 2 and 4?
Mirror images.
They're enantiomers. Oh, that'll be easy. We can just draw it as the mirror. H here, OH here, Cl there. That's 4. You see how they're mirroring? And indeed, if you look at 2 and 4, both are reversed. Okay? It's a little bit of cheating, but also just sort of give you some insight. Okay, last thing here's some terminology. Remember I said cis and trans is not useful because of that free rotation? Let's look at 1. If you looked at 1 in the perspective drawing, it looks like it's cis, the way we drew it, they were both bold.
Yes.
But see, you can rotate, and you can draw it trans, so which is it? This is it. The convention is to look at it in the Fisher projection and then say, are your high priority groups on each carbon? By the way, what's the high priority group here? Chlorine. What's the high priority group on this carbon? OH. In the Fisher projection, If your high priority groups are on opposite sides, trans doesn't work. We're going to call it
Real.
3O. This is also 3O. Because the mirror image of 3O is 3O, just like the mirror image of trans is trans. But if the high priority groups are on the same side, in alkene nomenclature you would call that Z. Or is it the same side? But here you don't call it Z. We call this what? Erythro. That's also erythro, because the mirror image of erythro is erythro. By going by this name, you don't get confused. Is it cis or is it trans? Is it cis? Okay. Here. Is it cis or trans? It's cis there and it's trans here, but it's the same thing. Well, what about if it's in a Fisher projection? If it's in a Fisher projection, the groups are on opposite sides, so it is 3O. And it's always 3O because we have given a more specific terminology. Okay? What is the relationship between 3O and erythro? That is, what's the relationship between 2 and 3? Is erythro and 3O enantiomers? Diastereomers. Erythro and 3O is a type of diastereomers, just like cis and trans. That's why here, in terms of type of diastereomers, cis and trans, but also erythro and 3O, type of diastereomer. Where do these terms, by the way, how do you remember these? I remember it like this. If you draw a capital E, the lines are on the same side. These three are on the same side of the vertical. Okay? Erythro, they're on the same side. If you draw a capital T, you got points on different sides. 3O, you have groups on different sides. That's how I remember it. Where does this terminology come from? It comes from back over here. If you look at a 4-carbon sugar, they have two names, threose and erythros. With erythros, the two OHs are on the same side. With threose, the OHs are on opposite sides. That's where the terminology originally comes from. How we doing, guys? All right. Most of this stuff is lots of information coming your way. You go think about it. You boil it down to okay, what do we need to know here? All right. Sometimes it takes me 15 minutes to fully discuss a topic, but then you can sum it up in 30 seconds. Okay. Because I'm trying to give you a good explanation. Not just, hey, let's memorize this stuff and go. Okay, guys, let's move on to number 2. It's going to be a lot shorter than number 1 was. How many stereoisomers is possible for number 2? How many chiral carbons? 2. many carbons do you see?
2.
I see 2 carbons. Yep.
Mhm.
2 to the end would be 4. Four max stereoisomers. Could you draw them all? Sure, just like we did before. Okay. If you draw them all and actually look at them and do everything we've done before, for example, are they really mirror images? Can they superimpose? You actually find in this case that there's only, not 4, there's only 3. Because if you draw all 4 on the board like we just did, if you look at them close, you'll see that 2 of them are actually the same exact molecule. Thus, there's only 3 total different molecules on the board. What's going on here? Okay? I think I want you to do this on your own because me just doing it, you're going to lose the practice, the struggle. Okay? There's actually only 3. Okay? Go through what we did, but figure out which 2 are actually the same. Why would something be the same? You're going to see mirror images. Are mirror images always different? Or are mirror images sometimes the same? For example, here, that's the mirror image of that. Are they different? No, these are the same. It's 2 identical paper clips. Remember what? When will the mirror image be the same? Brian, when will the mirror image be the same? Okay. Jennifer, when will the mirror image be the same thing? Anybody? When it has its own internal plane. Can you split this in half and have one half the same as the other? Yeah, it has an internal mirror plane. That tells you that the mirror image is going to be the same. You need to look for an internal mirror plane. Once you get your 4 drawn, step back and say, does one of them have an internal mirror plane? Because if it does, the mirror image is the same thing. Okay? Once you do that on your own, because you need to develop your own pathway to the knowledge. All right? Organize your thoughts. All right? I'm going to move ahead. We can look at that tomorrow. Okay, the paragraph number 3, I've really already explained that. There's 2 types of stereogenic centers that we're looking at. Chirocarbons is one, alkenes another. But are all alkenes stereogenic? No. On the quiz, there was one that was not, and that was the right answer. So alkenes can potentially be. You have to be able to know when an alkene is stereogenic. Okay? For example, let's look at this compound here. First off, how many chirocarbons does this glaucoma drug have? Anybody got it? Douglas?
6. 6, I believe.
6?
I think so.
I didn't get 6. I
4.
got
see
I
five.
got,
I got 4.
I only see 5 unless I'm missing one. 5? 5? Anybody get other than 5? Anybody?
Okay, I can see.
I got 4.
4? I think I see 5.
I see 5.
I see this one here. I see this one here. This one here. This one here. And that one there. Am I missing one? Douglas, how'd you get 6?
I counted the one that's off the CF3, the one that's connected on the bottom. Yeah, no, I was counting that one wrong.
That,
Yeah, I was wrong.
does that carbon have 4 different things attached?
It is not.
It only has 3. Also, what's the geometry of that carbon?
It's easy
2.
Trigger.
Trigonal
Oh.
planar. A planar object has a plane symmetry. Only a tetrahedral, or maybe there's something. A planar object is not going to be chiral. Not all. I reckon that's a plane, but the reason it's not chiral is because the top is not the same as the bottom. A planar atom is not going to be a site of asymmetry, because an atom is itself symmetrical. Okay? No, an sp2 carbon is not chiral. 5, okay? That's not chiral, is it? It's got 2 methyls attached. Since there's 2 methyls, there's symmetry at that carbon. And you can draw it however you want, as long as you've got 4 things attached, there's no difference. You can put methyls back, forward, wherever. But here's a difference, because the OH could be drawn forward, or it could be drawn back. And that would be 2 different configurations, and one would be R, one would be S. Okay? How many chiral carbons is 5? Okay? How many stereogenic centers does it contain?
32.
32. How many? No. You're looking at how many total stereoisomers. That's not the question. The question is not how many total stereoisomers. How many stereogenic centers?
7.
7, because that's a stereogenic center. This can be R or S, right? What can this be?
The trans.
Cis or trans, or E or Z. Okay? Now the whole thing is a stereogenic center. But also here, right here it's cis, but couldn't it also be trans? Yeah, I mean that's a stereogenic center. It has possibility for 2 different orientations. That's what stereogenic means. And so we have E or Z here. Now this one's shown as Z. But you can also show it as E. Where that's just shown generic. Of course it's either R or S. It can't be nothing. But you can show this. It's hard to show an alkene generic. So actually both alkene, are these alkenes stereogenic? This is cis. Boom. Can that be trans? No. You cannot be trans and still have a ring. Okay. I don't know if I addressed that in the video. If you've got a real big ring, like 12-membered, maybe you could be stereogenic. But a 6-membered ring, these double bonds are not stereogenic. They cannot be trans. It's physically impossible. Okay, now knowing that the total is 7, Derek,
124.
let me ask you this question. How many total stereoisomers possible? 2 to the 7, which is
124.
it 124? If 2 to the 7 is 120, 124 different stereoisomers. Okay, draw them all.
128.
Yeah, 128.
Yeah, 64.
Can you draw all 124? Well, one of them will be where all of these are R, and that's trans and trans. That'd be one. But then you can have all these R and that'd be trans and cis, that'd be 2. Then you can have all these R and that'd be cis and cis, that'd be 3. You can go through every variation. Then this could be R, 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 and that would be S. You get the point? If you do them all, it'd be 124.
256.
120?
128, right?
Is it 128?
Yeah,
Is that what you said?
I said 124, I was
Okay.
wrong.
2 to the 7 equals whatever this is. That's the answer.
And it's 256.
As long as something else going on, okay? Back up here, something's going on and there's less than max.
It's 256.
Okay, let's try to finish up here. Definition of diastereomers, we've already done that. Definition of epimers. Epimers are stereoisomers that differ by having only one center reversed when multiple are present. This is called an epimer. An epimer is a type of diastereomer. There's a specific type where only one is changed. For example, if we turn back over to the carbohydrates, we can illustrate this with those compounds.
So in that case, you got to have 3 or more stereocenters.
No, you have to have 2 or more.
If you have 2 and you reverse one, then it's just a diastereomer ring.
Epimer is a type of diastereomer. Let's look at this. What's the relationship between some of these carbohydrates? If you look at these carbohydrates here, these are all 6-carbon carbohydrates. They vary in the stereochemistry. This is D-allose. Are any of those the enantiomer of D-allose? The enantiomer would be where everything's reversed. If you keep the backbone the same, that would mean where all of these are over here. None of those are enantiomers. These are all diastereomers of each other if you look at them. For example, what's the difference in going from allose to altrose? Same, same, same. If you do R and S, these are the same, same, same. Right here. Okay? So what we have is only one center has been changed in going from allose to altrose. Since only one has been changed, what's the relationship? These are epimers. But they're also diastereomers. Because there's only 2 types. Okay, an epimer is just a special type of diastereomer. Since this is called the C2, 1, 2, these are called C2 epimers. That tells you that at carbon 2 you had a change. So now we can have some terminology. Glucose, what's its relationship to allose? They're epimers, but more specifically, C3 epimers. Okay, let's look at this. Allose and galactose, are those epimers? Allose and galactose?
No.
No, because 2 things has changed. These are not epimers. But they are diastereomers. Okay, guys, lab today, we'll finish this up. We'll begin alkyne chemistry tomorrow. Please work on that problem. Okay? We're going to introduce for that problem meso, the term meso. Hopefully there'll be good questions tomorrow. See some of you in lab today. Why don't we meet here? The lab each day, today and tomorrow. Let's meet here. 1 o'clock. Okay, guys, have a good day.